Hello, continuing on with part two of our evolution series. We get to natural selection, and natural selection requires three things. It requires, there we go, overproduction, variation, and selection. So we'll talk about each one of these. Overproduction is producing more offspring that can survive. Offspring must compete for limited resources. So we know that many animals will reproduce and lay more eggs or have more babies than will ever survive to be able to grow up to reproduce. Elephants, if every elephant born grew to maturity to actually have their own babies, within 750 years, there'd be 19 million animals roaming the earth. Fish give millions of eggs at one time. Sea turtles, 70 to 190 eggs at a time. Only 1% of them survive to reproduce. So first of all, we know of the hazards once they're laid on the beach, right? So they have to be laid on the beach. They all at the same time will crack open the egg and then try to get to the water. And there's lots of barriers that get them. Other animals and birds. Even there's lights now that are problems. So in South Florida, I know they were talking about city lights or even just lights from homes nearby where they get confused and don't see the reflection of the sun and the reflection of light on the water, and they are seeing the reflection of lights from the city, and they'll go the wrong way. So all different things that can prevent these sea turtles from surviving. Again, too, once they get to the water, they're little, and think of all the problems that they have to face there. Oysters will lay 60 to 80 million eggs at a time, and spiders, right? More little baby spiders can be produced than will ever stay alive, especially if they're in my house, because I kill them immediately. So Darwin's theory of natural selection includes also variation. So variation means that individuals in a population must have traits that differ. These must be inherited traits so that they can be passed on to offspring, okay? So here we've got some shells, and look at that. It's the same species of shell, just all different types of coloring and stuff, right? These shells will either help or help them stay alive or make it worse for them to be able to stay alive. We see that also in the variation of the moths, right, from our first video too. So here's a moth over here. So you can see there's moths in here you just can't see. They blend in too well, right? Those are the ones that are going to be able to live and survive and pass on. Then we have selection. So some traits make an organism more or less likely to survive. Individuals with a better chance to survive are said to have higher fitness. Individuals with a higher fitness leave more offspring. So I want you to look at this picture here and think of some things that would make either of these animals more or less fit to survive in their environment. Okay. So first off, hopefully you noticed that the color was different, right? The lion can blend in perfectly with the field and be able to sneak up on its prey. Whereas the color of the water buffalo, he stands out, saying, "Come get me," right? One thing you might notice are the horns on the water buffalo, right? If the lion was smaller, maybe he could fight off with those horns, okay? Another thing, check out their size difference. Even though the water buffalo is bigger, the distribution of the weight is different, right? He's got smaller legs and a thick top, and that lion is completely muscular, and can pounce and easily take that water buffalo down. The teeth of the lion, right? Perfectly made for eating flesh. And then there's also the claws on that lion, right? So it can grab and tear. So a lot of things here that make the lion a better fit for its environment, right? He has higher fitness to be able to take down this larger water buffalo. So this theory of natural selection includes adaptation. So over time, traits that increase their fitness or survival and reproduction will become more common. And it's not just in animals, it's in plants too. Roses and other and fruit-bearing plants like berries will have thorns on them, right? To try to ward off predators. Don't come and eat my seeds, right? The whole idea of the plant also is to reproduce and get seeds out there so that more can be made. So a lot of the stuff is warnings or trying to scare off predators from eating them, right? We've got poisons. We've got the smell of a skunk. Shells on snails, the stinging tentacles on jellyfish, claws. This is one where it helps them to get their food better, right? A roaring sound to be intimidating. Mimicry. So we have seen in nature other animals, similar but different species, but they take on the look of other animals within their species, within their types. So a snake that looks like a poisonous snake but is not, he just kind of mimics the colors, right? Pretty cool. Camouflaging, right? Blending in. Horns are a good adaptation, right? And then spines on plants too. So these are all things that animals have to either help them survive better and reproduce, whether it's hiding from predators or being the predator and getting the prey. Here is the reason why those giraffes, it was disproved.
We just had the most amazing family vacation.
Oh my God.
This is gorgeous.
Maybe the most violent giraffe fight ever caught on tape, for those of you who keep track of such things. Stunning video from the Discovery Channel shows two giraffes using their 6-foot-long necks as weapons to go after each other. ABC's Paula Ferris has the story.
Huge claws, sharp teeth, and aggressive antlers, all familiar weapons of the wild. But now, in this rare video, two unlikely fighters are sticking their necks in the ring. That's right, giraffes, the long-tongued, long-limbed, long-shot for prize fighter, battling it out. Watch as they jab their horns into each other, swinging their 500-pound necks with such force.
They're brutal.
But Toronto-based predator expert Dave Salmoni says not to worry.
It's a bit of a dance. The males know exactly where to stand, how to stand, and what the rules are.
Crews spent a month in Namibia, filming what they assumed to be gentle giants for Discovery Channel's new series Africa, when suddenly their subjects revealed another side.
People tend to think of giraffe as nice, docile, sweet animals, and they generally are. But they're designed for fighting.
These two males are fighting over territory and likely a mate, but not to the death.
The smaller, probably younger male will end up losing the fight, go away, get bigger, and then he'll get his chances.
So while we may expect fights from predators like these bears caught in a backyard brawl, or this lioness lunging at the camera, just remember, a seemingly cute face like this munching on leaves may be picking up the battle. For Good Morning America, Paula Ferris, ABC News, New York.
And that's the reason why the next generation of baby giraffes have longer and stronger necks, is because only the bigger and stronger giraffes were the ones who were able to reproduce to send those genes down. Okay. See if we can get back. There we go. So that was just proving Lamarck's use and disuse theory, right? So Darwin's theory of natural selection, a summary of it real quick. Our individuals are different and some variations are inherited. Organisms produce more offspring than can survive, and many that do survive do not reproduce. Organisms compete for limited resources. Remember back to Malthus's population theory, space and food. They'll fight for space and food. And then individuals best suited for their environment have the best chance to survive and reproduce. Others will die off or not reproduce. Okay. And then if we go back to looking at, let me see if I can move, I can't move this anymore. Okay. Ooh. Sorry, guys. Dang. Okay, technical difficulties there for a moment. Here we go. It's just cutting off the very bottom of this. And this is from the Galapagos Island. This is one of what Darwin had thought about a common ancestor coming from South American mainland, okay? So we're moving on to the concept now of common descent, of everything like coming from one organism or something and then breaking off from it. And so he noticed that the finches there, the Galapagos Islands, were very similar to one South American mainland finch. And then as the birds got to the islands, those island habitats changed so specifically. The food sources were very different too, and that eventually over many, many years, we ended up with different finches on different islands that looked totally different too. You've got brown-headed, white-headed, brown, black-headed, some very large heads, some small heads, and then the beaks are so different, right? But they all look like they came from this one kind of bird from the South American mainland. So Darwin put this theory into thinking of the big picture and going back to the beginning of something. In the beginning, there was one thing, and then it branched off into all the different types of life that we have. And so remember, this was just the part of the theories. This isn't proven yet. And so we can't go back in time. We can't see what happened and fill in those gaps. But this was his thinking. So in some ways, for evidence, to show some evidence of evolution. Now remember, evolution is just change over time. And direct evidence of evolution, we have fossil records. So fossils are remains or traces of organisms that have lived in the past. Different types of fossils, we have petrified bones, which are organic material that becomes a fossil through the replacement of original material and the filling in of the original pore spaces with minerals. So petrified bones the pore spaces have been filled in by minerals, and we get the same exact shape of what the bone was. An imprint is a track or a bone print, like in rock. A mold would be a fossilized impression made in the substrate. It is a negative image of the organism. Okay, so you can see this was a shell here at one time, and then the rock filled in around it, leaving that impression. Now, a cast is the mold filled in and then brought out. So if we took a mold and then filled it in with something, some sort of chalky material, right, that will fill it in, we can pull that out and we get a cast. So we get the actual 3D version of what left that mold. Fossils can also be preserved in tar, amber, which is just fossilized tree resin, or ice. There's some cool movies out there talking about things being preserved for a long time, right? Here is a fossil of an Archaeopteryx. This actually means old wing. It had the wings and opposable big toe of a bird, but the tail, teeth, and claws of a dinosaur. And this over here is like the rendition of what it thinks it would look like if you put the body muscles on it and feathers and such. Okay, we're not going to watch, I won't watch these videos. If you want to go back and save them somehow, you can, but it just shows a couple videos of them, one in China of discovering some dinosaur remains, and then one in Colorado just a couple years ago, right outside of Denver in a town called Thornton. They found some really cool dinosaur bones in one of their construction sites, and pretty cool. It's a beautiful museum. If you ever get there in Denver, I think it's Museum of Natural History there. Pretty cool. We've got some great dinosaur things here in Utah too. The evolution of the horse, this is pretty cool. So over time, so the higher layers of sediment, horse fossils became larger. If we start down here, this little thing here, let me see if I can move me. I can move me. I'll move me out of the way over here. Okay, so this was 60 million years ago. The horse was about the size of a dog, and it had 4 little toes on the feet, and the teeth were really small. And then 25 million years, we get 3 toes, and the toes are shortened. The teeth become bigger. The body becomes a little bigger. Next up, that's 40 million. 25 million years here. It's almost down to 1 toe. 7 million, there's no toe, right? It's just the hoof left. The teeth are huge. And then as of 3 million years ago, we found fossils of the horse that's more or less what we have nowadays, right? Although they have breeded them and we have special breeds, but this is what the horse would look like today with no toes there at all, just the big one single toe with a hoof, and then a huge tooth, okay? So the separate toes become a single-toed hoof. Teeth become adapted to grinding grasses. We know this from fossils. Pretty cool. Okay, where did whales come from and how did they change? So 15 million years ago, the spout on the whale was way down on its nose, lower. And then as the years changed, 25 million years, the snout itself has moved a little, like the snout before, if you saw it angled down more, and now it's a little higher, and that the blowhole is further back. And then now we've got the blowhole at the very top here, okay? So the thinking for this, why would this be an evolutionary advantage? So you think a whale, to get air, if it was on its nose, the spout would have to come up like this to release and to get air and stuff, right? So instead, it just can go like this, up and down in the water really easily, okay? That is a massive amount of animal to have to tip like this every time. So that spout has changed. Okay, and then we'll talk a little later too about other things that a whale has. That's pretty cool. So relative age fossils is layering of fossils. You have older fossils are found in the lower levels of sediments, and sediment layers sediment layers will form due to erosion, floods, wind, and temperature variations, right? And so as layers build on top of each other, the older fossils will be in the lower layers, the newer fossils will be in the younger layers. Newer fossils are deposited on top of older fossils in sediment. And so here's a picture of it on land. It also happens in the ocean as sediment layers on top of each other. The older fossils are on the bottom. Relative age position allows us to estimate a fossil's age compared to other fossils, okay? So we just can't tell by looking at this that it's so many million years old, okay? But we can say, well, this fossil found down here in this white layer is older than one of these fossils up here in the darker layers up above it. Okay, so here is a key and a map to kind of read of talking about relative age dating. Some questions to think about here. This is site 1 over here, site 2 over here. Okay, I'm going to move up here. Okay, so by looking at it, we can see this layer is here. This red layer is the same here. They've got the same kind of blue layer. This one is missing the yellow layer and this. And then we get this layer, light pink, and then an orange on top. So this one over here is missing this yellow layer here. And if we look over here, it says extrusion, lava. The slanted lines is lava. So it has a lava layer here, and then another one here. So this lava layer didn't get quite over to the second site. This first lava layer did hit this site, okay? So this one's further away from the volcano site, right? From this, at least this volcano. So that's something we can check by just checking the keys. We could say that the trilobite down here is an older fossil compared to a dinosaur. These are the dinosaur tracks up here, okay? A bird is a younger than a fish, which is found in the way lower levels, right? Okay. Also, by looking at this, we see this intrusion, this thing coming up, right? So this could be it could be maybe water coming up, right? Because sometimes we get water that seeps up, and then things can sink in, right? And if it was close enough to a volcano area, we could get this could be lava coming up, and then the lava spews out. Okay, so that's relative age dating, comparing how old something is to something else. It has to be comparative. Okay, on the geological time scale, it's based on radioactive dating and fossil records. Scientists have proposed a timeline for the history of Earth. They have proposed it to be 4.6 billion years old, okay? This huge amount of time was necessary for the slow process of evolution to occur. So we could see the millions of years differences in fossils with an Earth that long. A quick check for understanding. This is formed when a mold is filled in, the cast. Okay, organic material fills in with original pore spaces with minerals. This would be petrified bone. A way to estimate fossils compared to other fossils found in sediment, that would be relative age position. It already says, is a track or an imprint. Oh, a track or an imprint, right, is the imprint. And then fossilized impression leaving a negative image. If it leaves the negative image, it's the mold, okay? And if you fill it in, it's the cast, right? Awesome. We're stopping there. We'll come back with indirect evidences of evolution next time. Make sure your notes are all filled in. Email me any questions.